Elasticity is a favorite term in economics, meaning responsiveness. It's why supply and demand schedules are usually sloped, because quantity supplied or demanded usually responds to changes in price. Take ice cream cones. The more they cost, the fewer people buy. That's what the slope suggests. As the price goes up, fewer and fewer ice cream cones are purchased. As the price goes down, the quantity demanded increases. So consumers respond to price. How much they respond is known as the price elasticity of demand. The supply curve also slopes because of suppliers' responsiveness to price, with quantity supplied increasing as the price rises. So suppliers too show some price elasticity. If they didn't, the supply schedule would be perfectly vertical, a price elasticity of 0. That is, the same quantity of ice cream supplied no matter what the price. Similarly, if demand were unresponsive to price or totally price inelastic, the demand schedule too would be a vertical line with a price elasticity of 0. The same quantity of ice cream demanded no matter what the price. Notice, though, that when either schedule slopes and indicates some degree of elasticity, the actual angle depends on the scale. The angle's steeper if a $5 price is up here, but if we use a scale that puts $5 lower down, the angle is more horizontal. That's why elasticity is always measured in terms of percentages. Percentage change in quantity over percentage change in price. A calculation the textbook explains, and that the Discover Econ software allows you to practice. For our purposes, though, the importance of elasticity is how it helps explain the real world. So the rest of this segment is devoted to solving a real-world economic puzzle. Why, in the winter of 2000-2001, did natural gas prices spike to historically unheard-of levels? The first reason was the weather. It got so cold in my native New England, for instance, that even Frosty bundled up. Meanwhile, California was so hot that air conditioners overloaded the power grid, and in the Northwest it was so dry that hydropower plants couldn't provide extra power. Okay, so far so simple. In the winter of 2000-2001, severe weather and less energy from substitute sources increased the demand for gas. More demand, the demand curve shifted to the right. So the quantity of gas purchased rose suddenly from its then current level. Now, the way we've drawn this graph, it suggests that at equilibrium, price should rise modestly for a modest increase in demand. But in fact, the price spiked to over $8. So what's wrong with this picture? Well, for one thing, it visually misrepresents the price elasticity of demand for natural gas. So let's back up a step. The key question about elasticity is how elastic? That is, how responsive is demand, or for that matter supply, to changes in price? But remember, the answer is measured in percentages. Using percentages, then, let's look at Major League Baseball. In 2003, the average ticket price was about $20, average attendance about 28,000 people per game. What do you guess would happen if the league upped the price to $20.20 a ticket, a 1% price increase? Well, according to current data, ticket sales would drop by about 64 fans per game, a change of just under 0.25%. So quantity changes less than price in this case, resulting in an elasticity coefficient of 0.23. Now, an elasticity coefficient of less than 1 is the same as saying inelastic. So at current prices, the demand for baseball tickets is price inelastic. If a 1% price rise were to cause exactly a 1% decrease in ticket sales, we'd call the demand for tickets unit elastic, sometimes referred to as an elasticity of 1. And finally, if a 1% price increase were to cause more than a 1% dip in quantity demanded, we'd have an elasticity coefficient of more than 1, and demand would be price elastic. So now that you know this, let's see how you do in our Big League Elasticity quiz. Take a guess at elasticity coefficients for the following items at current prices. Bread, elastic or inelastic? Actually, 0.15, way less than 1 and thus inelastic. The demand for bread is not very responsive to price. Auto repair, elastic or inelastic? 0.4, still relatively inelastic. Movie tickets, 0.87, almost unit elastic, but not quite. Finally, a restaurant meal, 2.27, quite elastic. That is, Americans would cut back a lot on eating out if current prices rose. Now, elasticity coefficients are given at the current price, that is, at equilibrium. The reason is because of a frustrating fact about elasticity when it's depicted simply by a straight line, as here with the demand curve. On a straight line, elasticity changes as you move up and down. This demand schedule, for instance, is much more elastic at the top than at the bottom. Take price. It's at the top of its range. Thus, any move up here from, say, $10 to $9 is a relatively small change in percentage terms, 10%. However, you can see that this causes a change in quantity demanded from 1 movie ticket to 2. That's a change of 100%. When quantity demanded changes more than price in percentage terms, demand is price elastic. Meanwhile, down here, the opposite occurs. We're in the price range that changes a lot in percentages. It doubles from $1 to $2, yet the quantity demanded only drops from 10 to 9. So here, in percentage terms, quantity demanded changes less than price and is price inelastic, just because of where we are on the line. But all else equal, a linear demand schedule becomes more inelastic the more vertical its slope. Quantity demanded is less responsive here than it was here, which may begin to help illustrate our story, since the demand for natural gas could be unusually inelastic, which it would be easy to depict as unusually vertical. In plain English, consumers would be unusually dependent on this product, and therefore they wouldn't cut back much on their demand for natural gas if the current price went up. Consumers would demand this quantity when prices were low and just a little less when prices were higher. In other words, the quantity demanded wouldn't respond much to price. Or in personal terms, I'm not about to lower my gas consumption by turning down my thermostat, say, to 55. Natural gas isn't the only demand curve that's generally price inelastic. People are also generally unresponsive to price when it comes to life-saving medical care or addictive substances like tobacco or alcohol, which you don't tend to buy much less of when the price goes up. That is, the more you rely on something for which there are no suitable substitutes, the more unresponsive you are to changes in price, the more inelastic your demand almost anywhere on the schedule. So now have we solved the puzzle we started with? Why natural gas prices shot up so high in the winter of 2001? Well, not really, because look what happens to price when our now even more inelastic demand curve shifts to the right. It goes past the equilibrium point we drew earlier, when we told you there was something wrong with the picture, a demand curve that looked too elastic. However, even in this picture, price still doesn't rise nearly enough to reflect the enormous jump that occurred in real life. So what is still wrong with the picture? Well, let's look at the supply curve here. It looks relatively elastic, suggesting that suppliers are quite responsive to price, just as we'd imagine. A higher price, a lot more quantity supplied. And in fact, isn't that the beauty of a market system? Prices go up because we consumers want more of something. Suppliers respond to the cue by giving us more of what we want. Well, not necessarily, because in the short run, supply is often price inelastic too.
You see any natural gas drilling going on?
Back in 1992, when energy prices were low, Larry Strahan had taken us on a tour of drilling rigs standing idle on the Gulf Coast. 9 years later, prices were high enough to justify pressing them back into service to help increase the supply of fossil fuel for heating the Northeast. But the rigs were no longer available. After years of low prices, these very rigs had been recycled as scrap metal. 1,100 rigs were drilling in the U.S. by the winter of 2001, double the number just a few years before. But, says Strahan,
compare that with 4,500 to achieve the level we were at in 1983. Try that. I mean, to catch up, it's going to take us 2 years from the day we start drilling to go online with the natural gas we have.
Another reason supply hadn't responded to higher prices, he says, is that oil and gas drillers like Strahan himself had long since taken other jobs.
Oh, yeah, we can build drilling equipment. The problem is we can't get anybody to run it in today's world. So there's nobody left out here to do this.
So here at last is the answer to our question. What was wrong with this picture? Basically, both the supply and demand curves were drawn as relatively price-elastic straight lines, when in fact both were curvy and after a certain point almost completely price-inelastic. This may be more than you want to know about natural gas, but the real supply curve looks more like this. At low prices, supply responds a lot to changes in price because it's cheap to bring more gas to market. A small price change brings lots more gas out of the ground. But past here, today's wells and pipelines are running at capacity. There's no more gas in storage. To get more supply is almost impossible, so the curve becomes almost totally inelastic. Meanwhile, the real demand curve looks like this. We're not going to explain all the kinks, but the general idea is clear. Given the weather, there's a certain quantity of natural gas which Americans in the short run are willing to pay almost anything for. And when you combine inelastic supply with inelastic demand, you've got the potential for big price moves, big trouble. Especially for those of us subject to the big chill of a New England winter, as in our example, the winter of 2000-2001. To simplify, the weather was getting colder and colder, meaning more demand, meaning the demand curve kept shifting to the right. For a while, price rose gradually, but the demand curve finally reached the point at which, in essence, the gas ran out. The point at which the supply curve becomes almost totally inelastic. That was also the point on the quantity axis below which people that winter would freeze, below which, in other words, the demand curve was almost totally inelastic. When it got colder still, and of course people still needed to stay just as warm, demand shifted even more. The result was a stunning spike in price. Natural gas just about quadrupled in a month. And indeed, for a few days it went higher still, the result of market manipulation, it seems, to keep even more gas off the market. Less gas, a shift to the left, driving prices out of sight. In the long run, say economists, higher prices will enable gas producers to use new technology like 3D imaging of the Earth's crust to see quickly where it's best to drill. Producers will also be able to drill deeper, build more pipelines, and so on, and ultimately all this will allow them to produce more gas. Now, in terms of our graph, this means the supply curve, even though it too is relatively inelastic, shifts to the right. And given the inelastic segment of the demand curve, this should bring prices back down, way down. And by the way, eliminate opportunities for market manipulation. So in the long run, the market can be pretty effective at giving us what we want. So economics works in the long run. On the other hand, in the short run, a lot of people who can't afford the steep price rises due to inelasticity can get very seriously hurt. Which is why, when policy debates rage over the price of energy, it's so useful to know the economics behind the problem.